Okay, let's get started. So today we're basically continuing what is left for energy. Before we go about deriving gravitational potential energy and spring potential energy and the rest of energies, let me first solve the problem that was in the activity. It required us to have knowledge about vectors, which we did last time. So we are ready to solve it now. So let me pull it up first. Actually, it's here. So this was the problem, problem 8. We have an inclined plane, and we have all of these forces acting on the guy. And the question asks how much work done by basically all the forces, by friction, and then by the rope, and then by the gravitational force. And then what's the total work done, which is basically the sum of all previous three. So let's do that. Problem 8, activity 4. Okay. So let's start by drawing the free body diagram, which is already drawn, but let's have it here. So we have the gravity vertically downwards. We have two forces parallel to the ramp, the friction force and the tension force. Okay, and this is the guy here. This is gravity, which is Fg or M times G. We have this angle here as 60 degrees. And the guy goes for a distance equal 30 meters. Okay, down the ramp. So first question, how much work done by friction? Okay, so as always, we start by the formula for friction. So friction is F times D cosine theta. Okay. Theta here is not the 60-degree angle. Theta here is the angle between the force and displacement. So if we're talking about friction, then the angle between the force of friction and the displacement is 180 degrees, because the force of friction is pointing up here and displacement is down the plane, down the ramp. So they're pointing in opposite directions. So basically, this is F times D times cosine 180 degrees, which is just negative F times D. Okay. We have D equal 30 degrees. And we know the formula for friction. So this becomes negative mu mg cosine 60 degrees. This is friction times D, which is 30 meters. The mass of the guy is 90 kilograms. What's the coefficient of friction? 0.1. Okay. So this is basically negative 0.1 times 90 kilograms times 9.8 meters per second squared. Cosine 60 times 30 meters, which is some negative number. 1,323 joules. Okay, so this is the work done by friction. It is negative because, friction is pointing up the ramp. Displacement is down the ramp, so it's trying to oppose the motion. I think that part was straightforward. So the tricky part was for the next two parts. Next, we want to calculate the work done by the rope, which is basically the work done by tension. This tension force here. So to get the work done by tension, we need to get the tension first. We need to get the force of the force of tension. And we cannot do that until we decompose the force of gravity into components. Okay. So we will do what we learned yesterday. We will decompose our forces along the ramp and perpendicular to the ramp. So first, let me put the coordinates. Let's put the coordinates like this. This is X, this is Y. Okay. This is the force of gravity, mg, or let me call it Fg for now. Okay. This angle is 60 degrees. And we have, again, tension and friction. So I want to get the components of the force of gravity. Along the X direction and along the Y direction. Okay. So I want to get this part of the force of gravity and this part of it. Okay. So this part is Fgx because it's along X. And this part is Fgy because it's along the Y direction. And if this angle is 60 degrees, then this angle is 60 degrees as well. Okay. So we can use this triangle. This side is Fgx as well. It's the same as the side above. So if we isolated this triangle here like this, we have the hypotenuse as the magnitude of the force, Fg, and this side is Fgy, this side is Fgx. This is a right angle triangle, and this angle here is 60 degrees. Okay. So sine of 60 degrees is opposite over hypotenuse. So this is Fgx over Fg, right? Which means Fgx equal to Fg sine 60 equal to mg, which is 90 kilograms times 9.8 meter per second squared times sine 60. 763.8. Okay, so this is the X portion of the force. Okay, so this is pointing opposite to the tension. Okay, and we also have the Y component. Actually, I'm missing one force here. I'm missing the normal force. But it's not relevant anyway for this calculation. We only care about the tension for now. So the X part is sufficient. So we care about these forces now along the X axis. Okay. because now we know that the guy is moving with constant velocity, right? So acceleration is 0. So from Newton's second law, we have F net along x direction is equal to mass times acceleration along x direction. If the guy is moving at constant speed or constant velocity, this means that the acceleration is 0 and the net force along the x direction is 0. Okay. The forces along the x direction are the tension, friction, and now FGX. Okay. Where F is, did we calculate what F is? It's this amount without the 30. So it's some number anyway, and FGX is, we calculated above, 763.8 newtons. So now we can solve for tension. From this equation, we have T plus F minus FGX equal to 0, right? So tension, if we pull that to the other side, so that would be FGX minus F. Did you calculate F? Yes. 44.1. So if you do this calculation, you'll get that tension is equal to 19 point something, 0.7. So we managed to get tension. Now to get the work done by tension, this is easy. Tension is pointing up the ramp, displacement is down, so the angle is 180 degrees, so negative sign. So basically it's just negative T times D. So negative 719.7 times 30, which is equal to negative what? 20 what? 591. Okay. Joules. So now we got the work done by friction up here and the work done by tension down here. Both of them are negative. The final thing is to get the work done by gravity, and this is the easiest of them, because if we draw it again, force of gravity is here and displacement is here. If this angle was 60 degrees, then this angle is 30 degrees, right? So this is the angle between the force and displacement. So work done by gravity is equal to mgd cosine 30 degrees. So it's positive. So it's just 90 times 9.8 times 30 times cosine 30 should be appreciated. Thank you. 22,950 joules. Okay. Now to get the total work, you just add all of them. So work done by friction plus work done by tension plus work done by gravity with their respective signs. So friction and tension are negative works and gravity is positive work in this case. So negative 1323 joules and negative 21,591, and then plus 22,915 joules. I believe this was 2. Because all of this has to add up to 0. So rounding might,
I got 1.
huh?
1.
Yeah. Yeah, it should be 0. Because sometimes rounding make that error because we're dealing with thousands. You see 22,000. So if you get 1, so it's a sign that it should be 0. And the reason why it should be 0 is constant speed. So there is no change in kinetic energy. And we said before that the change in energy is equal to work done. So if there is no change in energy because constant speed, then the work done has to be equal to 0. Okay. So the tricky part for this problem was to calculate tension. To calculate tension, we needed to do this kind of decomposition of vectors. Okay.
When calculating tension, where did that 44.1 come from? Like, how did you calculate that?
This is friction. If friction is mu mg cosine 60. So if you substituted the numbers, you should get 44.1 newtons. Okay.
Okay.
Okay, now let's move on to the next part, which is potential energy. So in the previous lectures, we qualitatively discussed energy. We discussed what a system is. We discussed the many forms of energy and how they are characterized. We discussed the cause and effect relationship between work and energy, like change in energy in a system is caused by work done on the system. And then we defined what work itself is mathematically as force times distance times cosine of the angle between them. And using that and some knowledge from Newton's second law and kinematic equations, we arrived at a formula for kinetic energy, half mv squared. So today what we want to do is to do the same kind of thing to arrive at formulas for potential energy, gravitational potential energy, spring potential energy, thermal energy. It's all the same procedure in the derivation. And at the end, we will write down the conservation of energy law and discuss how to use it in solving energy problems. Okay. So let's first write down the important equations that we had so far. We had the work energy equation that the work done is equal to the change in energy. Then we defined work to be F d cosine theta. And last time we got kinetic energy half mv squared. Okay. This part is cause and effect relationship. This part is definition of work. Okay. And this part is kinetic energy. we will use the first two equations in all derivations today. So potential energy. So when two or more objects in a system interact, it is possible to store energy in that system. This energy can be recovered later as kinetic energy or thermal energy. But this stored energy itself is called potential energy. This is what we call potential energy, okay? So for example, when you lift a ball in the air, you put energy in that ball. So when you release it, it gains speed over distance when it's going to the ground, and eventually it has the potential energy that you put in it is converted to kinetic energy, and then eventually thermal energy when it hits the ground. And if you push a box against a spring and this spring compressed, then you store energy inside the spring as well, that when you release it, it will push back on the box and give it kinetic energy. So the stored energy is converted again to kinetic energy, okay? So potential energy is a stored energy that can be converted into other forms of energy. Okay. Today we will be doing gravity and springs for potential energy. These two forces are special because they allow storage of energy in the system. But there are other forces, other interaction forces that do not allow for energy storage. Friction, for example. Friction is an interaction force. If you have a box being pulled on a ground and this ground has friction, then this interaction doesn't store energy, rather it dissipates the energy and it goes in the form of heat or thermal energy that cannot be recovered later on, okay? So there are two different types of forces. We differentiate between them. We call those two forces, spring and potential, we call them conservative forces. Okay. The name comes from the fact that they conserve mechanical energy, which is the sum of kinetic and potential energy. They conserve this energy if they are in isolated system. And we have non-conservative forces like friction. So friction, on the other hand, is a non-conservative force. Okay. So conservative forces, they conserve mechanical energy. And non-conservative forces do not conserve mechanical energy, where mechanical energy is the sum of kinetic and potential energy. Sum of kinetic plus potential energy. Okay. So we will start with gravity and derive a formula for gravitational potential energy now. Okay. So derivation of gravitational potential energy, which we denote as U sub G. Okay. Let's imagine we have a ball, for example, we're holding it upwards. Okay. So initial height was y naught. Okay. This is the ground here, or the point y equals 0. So it's not necessary that we raise it from the ground. We can hold it like this and then give it some more height. So the initial point was y naught, and the final point was y final. Okay. So the ball went from here to here. Gravity is acting on the ball, right? And there is the force of your hand upwards. So F, let's call it FU. For simplicity, let's assume the ball is going up for a constant speed. So constant speed, lift. Okay. And the reason why I'm doing constant speed is I want to relate the force you exert on the ball to the force of gravity acting on the ball. Like they will be equal in magnitude because constant speed means no acceleration. So there is dynamical balance between forces. Okay. So these two forces will be equal. What happens? Yeah, these two forces will be equal because of constant speed. So Newton's second law tells you that the force up is equal to the force down. So your force is equal to the gravitational force, which is just mg in magnitudes. As you can see, it's different in direction, but in magnitude, both are the same. So to get a formula for energy, we have the change in energy equal to the work done, right? We start from here. The energy of interest here is the gravitational potential energy because there is no change in kinetic energy. It's going in constant speed. So speed is the same. So delta K is 0. There's no change in kinetic energy. Also, there is no friction. So there is no thermal energy. There are no springs involved here. So there is no spring potential energy. The only energy here is just gravitational. Okay. So this delta E, we can just write it as delta U. Delta U G. Okay. And this work done is work done by you on the ball. So from the definition of work, we know that work done is equal to the force times this times distance times the angle, cosine of the angle. And here, the force you exert is in the same direction as the displacement, right? So cosine of the angle is cosine of 0, so it's just 1. So it's as simple as multiplying the force times distance without doing anything else. So the work done by you is equal to the force times distance, which is equal to mg times distance, because we said that your force is equal to mg as well, right? Let's rearrange that a little bit. Let's just type it again here to have more space. We have delta U of G equal mg d, right? D is the displacement, and we said the ball started at y naught and then arrived at y final. So the total distance here, this is d, right? So d is just equal to delta y, right? Y final minus y initial. So delta UG equal to mg delta y. Okay. We can write that explicitly. We know that delta means change, so this is just the final potential energy minus the initial potential energy equals mg final position minus mg initial position. Okay. And as it can be seen from the equation, the corresponding terms are this. So you can conclude that the general formula for potential energy is just mgy. And this is the second important equation we have. Okay. Is the derivation clear? Okay. So there are some important remarks about this. We have UG equals mgy. Okay. This equation gives you the value of potential energy at a point. Okay. This equation is meaningless because we set the coordinate system arbitrarily. Okay. So if we have, let's say, I have this cup on the table. Okay, let's draw it here. So here is the ground. Here is the table. And I have my cup of coffee here on the table. Okay. So if I set the ground to be my y equals 0, and y the table is 1 meter above the ground or something, this is valid, right? This is valid choice of coordinate system. That would give me that the potential energy at the ground equal to 0, right? And potential energy at the table is equal to mg times y, like mass of the cup. Let's assume the mass of the cup is 1 kilogram and y is 1. So this is just 1 times 9.8 times 1. So it's just 9.8 joules. Okay. However, I could have chosen the table to be the origin and set y equal to 0 here and y equal to -1 here, right? It's just a choice of coordinates, because coordinates are not in nature. We choose the coordinates to assign values to position, as we discussed in kinematics. So if I did that, I would have potential energy at the ground being equal to -9.8 joule, and potential energy at the table equal to 0, right? So by choosing the coordinate system differently, I managed to get 2 different values for a quantity that is supposed to represent a physical quantity. So this doesn't make sense because physical quantities are in nature. They shouldn't depend on which coordinate system I choose. They are independent of my choice. What is independent of coordinate choice here is the difference between the value of potential energy from the table to the ground. So if you did this as UG at the table minus UG at the ground, in both cases, you will find the same number. So in the first case, we had U ground equal to 0 and U table equal to 9.8. So this is 9.8. And in the second case, we had the table being 0 and the ground being negative 9.8. So still we get the same number, positive 9.8 joule. So the whole point of this discussion is to convince you that potential energy at a point by itself is not meaningful. We need to talk about differences. We need to talk about the difference in potential energy between 2 points, okay? Also, that gives us the freedom of choosing any point as a reference point and set the potential to be 0 at that point and measure with respect to it. So, physically meaningful is the change in potential energy, which is equal to mg delta y, because delta y doesn't depend on the coordinate system. Delta y is a distance you can measure with a ruler independent of your choice of coordinates. You can shift the origin wherever you want, but the distance is the same. This pen doesn't change if I measured it from here to here or from there to there. It's the same length, okay? Now that we understand that what's meaningful is the difference, we can set the ground by definition and for convenience to be the 0 potential. This is at y equal to 0. Okay. So if I substituted that into the difference equation here, I will get that U of G at any point y, let's denote it, let's call it at height h, minus UG at the ground equal mg h minus 0, right? Right, I just substituted this definition into the formula above. So we defined the ground to be the 0 potential energy. So we get that the potential energy at height h is equal to mgh as measured from the ground being our reference point. Okay. So this equation by itself has implicit assumptions in it. It assumes that we're measuring with respect to the ground as our 0 potential. Okay. So this was the first remark. The second remark is that the gravitational potential energy depends only on vertical displacement. or vertical, yeah, displacement. It doesn't depend on horizontal distance. Why is that? Any thoughts?
Gravity doesn't act horizontally?
Sorry, what's that?
Is it because gravity doesn't act horizontally? It acts
Yeah.
vertically?
Yes, because gravity is acting vertically. So any work done is coming from the vertical part, because FD cosine theta, if gravity is acting vertically and you move horizontally, then the angle is 90 degrees. So cosine theta cancels, gives you 0. So any contribution from the horizontal part vanishes and you only get the vertical part left. This is very helpful because if you start moving from here and arrived here, let's say this is the ground. Okay. This is point A and this is point B. This height is h. If you go this way, or if you go this way, or if you go this way, all paths don't differ from each other in the change in potential energy. You will have the same difference in potential energy no matter what path you take, because all horizontal contributions vanish and you only get the height. As long as you arrived at the same height, you got to the same potential energy. Okay. This allows us to solve very complicated problems that we could not do with Newton's laws. Because in Newton's laws, we care about the path, we care about the forces. So if the path is different, we will have different normal forces and we have to decompose all stuff. For example, the inclined plane problem, we had to decompose the forces. But if we're doing it only with potential and kinetic energies, potential energy doesn't care about which angle is the incline. It only cares about the height. Okay. Yeah. So that's it for gravitational potential energy. The formula is mgh, where h is the height from the ground, and it only depends on the vertical height. So I will again write down the equations that we have so far. We have kinetic energy being half mv squared. And we have now potential energy from gravity equal to mgh. So those are the energies that we got so far. And the tools we use to derive all of these equations are this cause and effect relation between the change in energy and work, and the definition of work as the force distance times cosine the angle. So those are the tools to derive those. Okay. We will use them again now to derive the spring potential energy. Same procedure. We will do it for all energies. Spring potential energy. We denote that by the symbol US. Okay, U sub S. So we will derive it by assuming that you're pushing on a spring, compressing it a distance x. So this is the spring in the beginning. This is the equilibrium position of the spring. It's not compressed, it's not stretched. And then you push on it to get it to this distance. So This is the compression. The compression amount is X. Okay. So this is the force you act with. Let's again call it Fu. You do work on the spring, so you store energy in it. From this relation here, when you do work, the energy changes. Again, assume frictionless, assume there is no assume it's frictionless surface on the table. No change in gravitational potential energy because it's on the same level, so the height doesn't change. So again, the only thing changing is the quantity we want to calculate, which why we set up the problem this way. So the change in energy is just the change in spring potential energy. And this is equal to the work done by you on the spring. Okay, same procedure. Now the definition, the work done by you is equal to, let's first discuss the force. What's the force of the spring if it's compressed? Huh? Yes. Yeah, exactly. So the force you exert on the spring is equal in magnitude and opposite in direction to the force of the spring. Okay, let's just denote it F sub S. F sub S, the force of the spring, is equal to negative K delta X or negative KX. The spring force is equal to negative Kx. K is the spring constant, which measures the stiffness of the spring. How hard is it to compress it or stretch it? So the greater K is, the harder to compress the spring. This is usually given, you don't calculate it. It's like the mass, like when mass is how hard to move an object, this is how hard to compress or stretch the spring. So it's equivalent to mass in some sense. And X is just the compression or stretch in the spring. So then the force exerted by you is positive Kx because you're pushing on the spring, okay? So Fu is positive Kx. Now we want to do the work done by you. So we know the work done by you. Usually it's equal to Fd cosine theta, and I will ignore cosine theta because all the examples we're giving today is same direction. Force is in the same direction of displacement. But this relation was for a constant force, so the force doesn't change. But this force is changing with position. You see, if you're standing at x equals 0, there is no force. If the compression is 0, then there's no force. If the compression is 1 meter, then larger force. If the compression is 2 meters, then even larger force. So the force is not constant. So to avoid that, we will deal with the average force, just to be safe, because this definition was for a constant force. So the average force, let's assume we started with no compression at all, and then we compressed it to amount X. So the average force is first force plus the second force over 2, like a statistical average, okay? So Kx plus 0 over 2. And the 0 because there was no compression in the beginning. So the average force is half Kx. Okay. So I will substitute that here. So we will have half kx, and the distance covered is x. So this is half kx squared. And again, the work done by you is the stored energy in the spring. So this gives us the formula for the spring potential energy stored in a spring. Delta US is equal to half kx squared. And I will drop the delta because we're already assuming that the potential energy is 0 at x equals 0. So this is the potential energy when the spring is compressed or stretched with amount x. This x is not like if you have a moving cart and this cart has a spring inside it and it's moving along a line, this x is for the compression of the spring, not for the motion, okay? So let me draw the picture again. If this is the spring and you compress it by a certain amount, this is the x we mean. Okay. And same thing if you stretch it by that same amount. You still get the same stored energy. Okay. And that's the third energy we have. We had potential energy for gravity and we had kinetic energy. So let's put them all together. Half kx squared, k equal half mv squared. Ug equal mgh. And us equal half kx squared. There is one more energy that we're going to derive and then discuss conservation of energy. After that, we will be ready to solve problems. Thermal energy. So we briefly discussed thermal energy in the first lecture on energy. We said it's fundamentally related to the motion and jiggling around of the molecules and atoms in the material. So fundamentally, they are just sum of kinetic and potential energies at the microscopic level. And then the macroscopic effect is that we see it as a thermal energy. But we discuss it as a different type of energy nevertheless, because we're doing macroscopic physics, not microscopic. And this is usually associated with friction, okay? So let's assume we are pulling a box on a friction, on ground that has friction. We are pulling that box with force along the same direction of displacement. So friction is acting to the other side, Fk, and assume that the object is moving at a constant speed. Again, the reason why I'm using constant speed is because I don't want any change in kinetic energy, because I want to focus only on thermal energy. It's on the ground, so there's no change in gravitational potential energy. There are no springs around, so the only change in the total energy is coming from the change in the thermal energy. Okay. What is the work done by this big F? It's just force times distance. It's as simple as that. And this is the change in the thermal energy. Usually it's denoted delta X instead of D. So let me rewrite that. The friction force times delta X. I didn't even derive anything. This is the formula for the change in thermal energy, not for the thermal energy itself, because we don't know what the formula for thermal energy itself is. The only thing we can measure realistically is the change in thermal energy. So that's why we think of that as sufficient. Those are all forms of energy that we're going to deal with in this class. And now we're going to put them together and discuss the conservation of energy. So conservation of energy. So far, we got kinetic energy equal half mv squared. Those are important formulas that I write down every time. Gravitational potential energy is mgh. Spring potential energy is half kx squared. And finally, the change in thermal energy is friction times the displacement along which friction is acting. Those are the energies that we deal with. Okay. Now, we said that the change in the total energy of a system is equal to the work done on it. This symbol E without anything subscript or superscript or anything is the total energy. Okay. So the total energy is the sum of kinetic energy plus potential energy plus thermal energy plus spring energy plus everything. Okay. So the change in energy is equal to the sum of the changes in every type of energy. So this can be written as delta K plus delta U sub G plus delta U sub S plus delta E thermal equal to the work done for the four energies we have. Okay. It's helpful to write that as before and after equation, like initial and final, instead of the deltas, like separate each side and put the initial values in one side and the final values on another side. This is helpful for solving problems. So let's do that. We have K final minus K initial. I'm using naught for all quantities. Do you want me to use I instead? It's fine. Okay. I'm just trying to stick with a notation. mg h final minus mg h naught plus half kx squared final minus half kx squared naught plus this one. I will not write it as final and initial, as I said, because we don't know how to measure initial and final points. So I will leave it as a difference. And this is equal to the work done. Then I will rearrange the formulas. I will take all the initial values and remove them to the other side with a positive sign instead of a negative. Then I'm left with K final plus why did I write the formulas right away? Wait, I don't want to put the formulas now. I want it as UG final, UG initial plus US final minus US initial. Same thing, I just don't want to substitute the formulas now. Then this is equal to U final plus US final plus change in thermal energy equal to initial values plus W. This is the most important equation in this chapter. Okay. What does it say? On the right-hand side, we have the initial inputs. So you have the initial value for energies and the work input, the work done on the system. On the left-hand side, you have the final values for energy and the change in thermal energy. Okay, so you start with the system with certain energies, you do work on it, the energies change, and you gain thermal energy. Okay, this is not conservation of energy yet. This is energy change. Okay, this is the most general equation you can get for energy for the forms we have now. Of course, you know the values above, K, UG, and U sub S and delta E thermal. So you can just put these and have numbers. Everything else I will say now is a special case from this equation. So let's see the three important cases for this equation. First, if we have an isolated system, let me just denote that these are special cases. Important special cases. Isolated system. What does isolated system mean? No energy transfer. How do I write that in a quantitative way? Yes, exactly. So isolated system means there is no work done on the system by the environment, which gives you the equation above, but without the W. The equation above without the W, I will just copy it. Copy, where is copy? Copy. Then paste it again here. But without this W. This equation is conservation of energy. Because you have all the initial energies are equal to the final energies. And if you're confused by this delta E thermal, if you break it down into initial and final, assuming that we could somehow measure the initial and final values, you could pull one of them to the other side and say, okay, the initial value of the thermal energy plus the initial value of the kinetic energy plus the initial value of potential energy equal the final values. Like the sum of the initial values equal to the sum of the final values. Okay? So this is the law of conservation of energy. Even simpler, so this was case one. Case two, isolated system and no friction. In this case, there is no change in the thermal energy. And again, there is no work done. This leaves us with what's known as the conservation of mechanical energy. And that's what we said, conservative forces conserve mechanical energy. So when there is no friction, we have conservative forces, and then sum of kinetic plus potential energy equal to the final sum of kinetic and potential energies. So in the isolated system case, again, you copy that down, put it here, but without the delta, without delta thermal here. So with a big equal sign. This is conservation of mechanical energy, and this is the most common equation for conservation, because most of the time we don't put friction into conservation problems. So this is the common equation. Also, if you're not dealing with springs, then you only have kinetic and gravitational potential, Kf plus Ug, F equals K initial plus Ug initial. If you only have spring and kinetic and the motion is happening on a flat ground, so there's no change in potential energy. So you can play around with the equation and deduce from it all you want. The most general equation, as I said, is this one. And depending on the problem you're solving, you will have many quantities equal to zero in that equation. So you will not end up putting all of these values together, but this is the most general one. Not again. At least I gave you the conservation law. Let me see what happens. So this is the equation that we will use in solving problems. Now, let me just give you one last thing before doing problem solving, just to get done with the chapter, which is power. And then we will come back to solve problems. I don't have an activity, but I have 4 problems. I will present them on the screen and we will solve them together. So power basically is the rate of transfer of energy, okay? So we knew that when you do work on a system, this work is transferred as energy to the system, but it's not always done at the same rate. So you can transfer energy to the system on a very long period of time, or you can do it instantaneously, not really instantaneously, but very fast. So this is characterized by what we call power. It's the rate of energy transfer. So power, it's denoted P, is equal to the rate of change. So it's delta E over delta T, meaning the change in energy divided by the change in time. It's like if you remember velocity, was change in position over change in time, which measured how fast this distance is covered. So like analogously, this is like a velocity. This is like a speed of how the energy is transferred. Okay, just analogy. And we know that delta E is equivalent to W. So this is also an equivalent form of the equation. The unit of power is joule per second. Okay, so this is the unit. Joule per second, but this is not the common unit. Joule per second is given the special name watt, big W, okay, or what, like you spell it out, but usually it's just big W. And the value that you usually see is kilowatt. So kilowatt is just 1,000 watts. Okay. This is power. Sometimes you see the units of energy given in kilowatt hours, right? So I gave you a problem in homework, last problem, and I gave you that for each kilowatt hour, there is a price you pay, and then if you left something on for amount of time, how much does it cost? So the unit kilowatt hour is unit of energy, not power. This is unit of energy because it's unit of power times time. And if you look at this equation, power times time is energy, okay? So if you have 1 kilowatt hour, this is, how many joules is this? Let's calculate it. This is equal to 1,000 watt hour, which is equal to 1,000 joule per second times hour, and hour is, we can convert it as usual, 1 hour equal 3,600 seconds. So the hour cancel and the seconds cancel, and this is 3,650 joule. So it's energy. 1 kilowatt hour is this amount of energy. It's 3,600,000 joules. Okay. You will not memorize this, of course, but I'm just showing you it's the unit of energy. So whenever you see kilowatt hour, this is the amount of energy. So if I tell you, you pay this amount of dollars for 1 kilowatt hour, you know that if you consume more energy, you pay more. You pay more for that. Okay. This is relevant for last problem at homework. This is all I have to say about power. Now let's go back to conservation of energy to see how problems are solved. Let's do a simple problem. Let's imagine we have a compressed spring. You compress a spring to a certain amount, okay, from equilibrium condition, from equilibrium position. So let's say you stretch it for 10 centimeters, okay, and you attached a block to it, a block of mass M. This mass is equal to, let's say, 2 kilograms, okay. Then this is the initial situation. So we call this before. And then I asked you, what's the speed after the spring is released? What's the speed of the block after the spring is released and the block leaves the spring? So I will draw another picture with the spring not stretched now, and the block is not in contact with the spring anymore. So the block is moving with some unknown velocity that I want to solve for, V final. And this is the situation after. Okay. This is the very first thing you want to do when you solve energy problems, is to draw a picture for the situation before and the situation after. Then we want to use conservation of energy. So first we ask, is there any external work done on the system for this problem? It's a frictionless table. Okay. Let's assume these are the inputs. It's a frictionless table. So it's a level table, frictionless. So let's write down the most general equation. Let's copy it down and then see what remains of it. So first question, is there any network on the system? External work? Any suggestions? Yeah.
We're having to push it in.
Sorry, what's that?
If we're having to push in on the spring, that like
I'm assuming you start with the spring already compressed.
Oh.
So it already has the energy that you put in it and you left it compressed.
Okay.
So at the time being, there was external work to put the energy in the first place. But starting from this point, when it's already compressed, there is no external work done. Okay. So that's first thing that vanishes in the equation. So this is zero, external work. What else is zero? Yeah.
Potential energy of gravity. Staying the same one.
Yeah, exactly. What if I put this table like 10 meter high?
No.
Still the same, right?
Stays,
If it stays level, it doesn't matter where I put it. Even if I put it on a mountain, it doesn't matter. As long as we are at the same level, this will cancel from the same side. It's not because they're zero, but because they cancel with each other. They stay the same. So if I'm adding 1,000 here and I'm adding 1,000 over there, so they cancel anyway. What else? Why? Yes. There is no friction acting on the block, so this is also zero. Okay. Okay, now we have 4 quantities left. Do we have any zeros again? We have any more zeros? Yes, we have initial kinetic energy being zero because it was at rest, starts from rest. So this is zero as well. What else? Why?
There's no more energy stored in the spring.
Yes, no more compression. It goes back to equilibrium position. So final spring is zero. So all you're left with is that the final kinetic energy of the box is equal to the initial energy that was stored in the spring, which makes a lot of sense. if you compress a spring, it has a certain amount of energy. This energy goes to the kinetic energy of the ball. Nothing else is happening, right? So this complicated equation just boiled down to this simple relationship that when we write down what the kinetic and potential energies are, this is just half mv final squared equal to half k x squared. We have the mass is 2 kilograms. The distance of compression is 10 centimeters. Be careful to convert everything into SI units, into meters, kilograms, and kilograms and meters. I didn't give you the spring constants, which you should be given. So let's assume the spring constant is 10 newtons per meter. Okay. Spring constant is always given. If I didn't give it to you, then I just forgot. Okay, now let's substitute these numbers in, but just let's cancel the halves because there's no reason to carry them around if they are on both sides anyway. So 2 kilograms times v final squared, which I want to solve for, this is my unknown, equal to 10 newtons per meters, times x squared, which is 0.1 meter squared. This gives me v final squared equal to 10 times 0.1 squared over 2. Can you calculate that for me? I lost my calculator. Yes. Huh? The rate is 0.05. Yes. Then you take the square root. 0.224 meter per second. Which is about 22 centimeters per second. It's pretty fast. So this is a typical energy problem that you are given the initial configuration and you're asked to get the final velocity or something. Okay. I will give you 4 problems to work on. Do you want to take a break first? You can take a break for 5 minutes or 10 minutes and then come back to work on problems.